So welcome to lecture 6 in this series. And now we are up to conduction and convection, the final component of this energy balance analysis. And because this follows the same principles as transpiration, there's a lot of things that it takes less time to explain these principles, because it's also flux is the driving gradient divided by the resistance, that ratio. Remember, in the case of the psychometric chart, we spent a lot of time talking about how to calculate the driving gradient, the leaf-to-air vapor pressure difference. That requires some calculations. In the case of conduction and convection, however, this is real simple because the numerator is just the delta T, the delta temperature between the object and the air. So it's, if you know air temperature and you know the surface temperature, both of which we measure, we know the numerator for sensible heat. So in a minute, I'm going to talk about how we calculate the resistance. Now this is much more complex in conduction and convection. It's complex in transpiration too, because this is stomatal opening, a biological phenomena, but here it's physical phenomena that determine that. So let me take a tiny sidebar before I talk about that. We've pulled up here the Environmental Observatory on the Utah State University campus, and here's a live camera showing it. And if we watch this long enough, some student will walk through the picture right here. This has a whole series of graphs that demonstrate all of these principles. It's got net radiometers and long wave. We talked about this in a previous lecture. But here's the current past 2 days of temperature. Yeah, there's some people coming by. And what's fascinating around here is this blue line is campus. The red line is where we're at right now, which is the middle of the valley. And the red line is airport CSI. And if we tell people Campbell Scientific, not everyone in the valley knows where Campbell Scientific is. So we put airport/CSI, but the data from CSI is far superior to the airport data. So we don't actually use the airport data. We use the CSI data, but we tell them it's the airport. That's why it says airport CSI. But this night, like so many other nights around here, it's just everything, our weather, because of our changes in elevation in our valley, are just fascinating. Here's the green line, which is the top of Logan Peak. And anyone can walk outside and see this weather station up there. We're in July, it's finally getting warmer on Logan Peak. But look at the difference between campus and Campbell Scientific. And we're at maybe 4 degrees C colder in the middle of the valley last night. And look at this night. Last night, we got to 9 degrees C here at Apogee and Campbell Scientific, which are right together. Oops. And campus only got to 16. There was a 9 degree Celsius difference in temperature last night, which is an inversion. And it was colder here. An inversion would trap the air and potentially we'd have polluted air, but the sun came up and it warmed it right up, and a few hours later the inversion went away. And this is the summer. In the winter, these red and blue lines get below the green line and stay there for days at a time. But this is a fascinating difference, and what happens up in the top of Mount Logan is it just never warms up. Here we warm up to 30 in the day, and there they're barely warming up to 16 or 18 in the day. That's just the temperature. This shows wind speed, barometric pressure, and then solar radiation. These are nice clear days. You can see this is getting to 1,000. It looks like if we looked out the window, I guess there ought to be a few clouds, and there's a few clouds. If you have this, you actually don't have to look out the window. You can just see what's going on outside by looking at the graph. Here, clouds. Now we're at 1,116. There's some reflection off the clouds. We're going above our 1,000 watts per meter squared. This is where it's located on the campus. Let's look at a few of these because they demonstrate some of these principles so well. Dew point and humidity. So there's the air temperature and the dew point temperature. We have dry air, so the dew point actually is below zero some of the time. Look at this. Absolute humidity, relative humidity. Absolute humidity has a few fluctuations, but day and night, it's generally a flat line at about 5 or 6 grams per cubic meter. Relative humidity, down in the day, up at night, down. Cycles because of air temperature. After you get these principles, you just love seeing how they work and interpreting the data on this thing. All of these graphs have one day, and then you can call up the past 7 days. We're working on a new revision of this that's a lot more sophisticated. The whole campus is going to a better internet display that this will automatically scale to fill people's screens much nicer. We talked about barometric pressure, how much that varies. Let's call that up. This is one day, this is adjusted to sea level. Everybody adjusts to sea level so we can make maps of the pressures, the highs and lows. Even though this is here, it's corrected to sea level, so the barometric pressure is going down. This is more interesting in 7 days. These are electronic barometers, so it goes up. We were at a real high pressure, now we're going down for the past 7 days as those fronts come through. One of the most interesting things about this station is carbon dioxide concentration. That's wind. There we go. Here's CO2 on campus. So we're coming along here, low 400 ppm, and a big spike here, and another big spike here. Is that people breathing on this sensor, people driving their cars by the sensor? No. This is canyon winds. The canyon winds come out of the canyon and they have clean air right out of the Cache National Forest. All that photosynthesis cleans the air. And look what happened here. 9 p.m. the wind, the wind shifted. Right here is canyon wind. 90 degrees is coming out of the canyon. That canyon wind died about 7:30 this morning, and it shifted, and we got a puff of wind from downtown Logan, and it spiked the CO2. And we got another spike here. And now finally it's all the valleys clearing out. We see this every day. The canyon wind is low CO2 because of photosynthesis in the summer, and then the canyon wind dies and the valley air shifts up and we get a spike in CO2. And partly that's governed by photosynthesis, so here's the photosynthetic photon flux that drives that, and then wind speed. Surface temperature. We talk about calculating surface temperature. Most people don't realize how different surface temperatures can be than air temperatures. We're talking about delta T right here for driving conduction and convection. This is 2 replicate Apogee infrared sensors, and the red and green line pointing east and west.
Pointing at what?
The ground surface.
Grass?
Grass. Yes, this is irrigated turf. Yep. So let's jump back and we'll come back to this. If it should call up here in a second, and I can show you exactly what they're pointing at. Not coming up, but they're pointing at the irrigated turf. Surface temperature. So last night, and we're going to talk about this in a minute, way below air temperature, several degrees C below air temperature. It was a clear night. They're radiating to outer space, so they get cold. The sun comes up and suddenly they're warmer. And today we're only getting 4 degrees C above air temperature, But I have seen this go as high as 10 degrees C above air temperature, the turf grass surface compared to the air temperature. So it tells you how big these surface temperature fluxes can be. And this is irrigated too. It's lush and irrigated. One of the comparisons that we do up there is between shields. This is a graph of replicate matching tiny yellow bead thermistors. One of them is in a traditional gill shield, and one of them is in an Apogee aspirated shield. So this is the last 24 hours. And you can see at night they're virtually identical, and there's no flux. And here's the temperature differences in the day. And yesterday, for a little bit, we had 3 degrees C difference, but most of the time it was down around a 1 degree C difference. And this is a small sensor inside that shield. So you can track that, see the differences. Net radiation, we already talked about this. This is all the principles and all the calculations. This is intermittent clouds going on right here. Here's albedo of that grass up there through the day. And what did we say, 0.23 about for albedos? You know, this is just a hair above 2. It's slightly higher in the morning, and it goes down slightly in the afternoon. Right now it's 0.21 albedo of that turf grass. What else do you want to look at? One of the unique features of this is atmospheric visibility. This is a Campbell Scientific sensor. Most of the time it's very clear. A fleck of something got in there for these downward spikes. 32 kilometers is the max. That's real clean air. This is something that we watch a lot in the winter when we have inversions. How low does the visibility go? And this, I've seen this in the worst days of winter to go down here to 5 and 10. And then the inversion blows out and it's clear again.
It's interesting because those lasers are tuned to water. So we've always been curious to know what you end up with the conversion.
Yep.
You're not supposed to detect smog.
Well, this one is the reflection of light. The question is, these are tuned for water, and would they affect other things? This one's the reflection of light off of particles, which is highly correlated with human vision. So the Campbell Scientific England people are expected to pick up particles in the air, not just water vapor. It's any kind of particles. It's not too interesting because it's summer. Here's 7 days. There's a few spikes. It's summer, but it's pretty constant. Temperature, thermistor shields, solar radiation. That's just the shortwave radiation. I think we looked at that. This is multiple replicate sensors on here, and they're all reading very close to the same thing. It's comparison of technologies. This also shows power budget. I won't go through this thing, but for people understanding solar-powered stations that take a lot of power, it shows the energy going into the battery and coming out of the battery flux night and day. This station has a lot of sensors that take a lot of power. So power management's a big deal, and it's full of algorithms to turn stuff on and off depending on power availability. And this is made possible by the Campbell Scientific CH200 power management system. That gives us a lot more data than we ever used to have. ET and VPD, which is what we're talking about, here's calculated. Here's the vapor pressure deficit between just the air and then between the surface and the air, the turf surface. So we get down to less than 1 at night and get up to 4 in the day. And then we run the Penman-Monteith equation, and here's evapotranspiration calculated through the day, yesterday and today. And then a long discussion about ET right there. This shows historical data. There's a lot of graphs on here. Here's air temperatures the last 2 years. Summer, winter, the min and max for each day. So lots of data and combined climate data and data that the goal is to help educate the campus community for weather data. And so people get interested in this, and because this has a camera, you can see when somebody stands there. This is a touchscreen kiosk now in front of this, which has its own set of graphs, and it's particularly edifying to see students come and look at that and study the graphs and look at the sensors, and it's a great educational opportunity to teach people about weather. All right, back to, from that sidebar, back to sensible heat. So the numerator is delta T. The resistance is determined by the thickness of a tiny layer of dead air right next to all surfaces. And everything has that. This board has that, our skin has that, and that dead air is just like a thermal pane window, a tiny layer that resists the movement of heat. And if that layer was gone completely and the resistance approached zero, things would immediately equilibrate with the air. But they never do immediately equilibrate because of this little resistance layer. So if we take just the resistance, now this is called resistance BL, boundary layer, because it's a thickness. And what we're going to calculate is how thick this airspace is. It's on the order of millimeters. It's not a thermal pane window, might be 1 to 2 centimeters to trap dead air. This is more like less than a millimeter. So not surprisingly, this is inversely proportional to wind. That's wind speed. So there's the fundamental concept. It's proportional to wind. But like lots of heat transfer and a lot of principles of wind, it's not directly proportional. It's proportional to the square root of wind. So if the wind doubles, heat transfer doesn't double. It goes up by the square root. So it's a nonlinear function of wind. But there's one other parameter along with wind that's equally important in here, and that's in the numerator. So if I put proportional, inversely proportional to wind, this is width. The width of the object that the wind is blowing over. And now in this analysis, it's a flat object. We can do this for cylinders and ovals and different shapes, but for a flat object, it's proportional to the width. So as the width gets bigger, the heat transfer gets less. And you can imagine a pine needle would have very efficient heat transfer because it's thin and little, and a banana leaf that's 1 meter wide would have very bad, very poor heat transfer because of width. Now, same thing as wind, it's also proportional to the square root of width. So these are the two variables in this that determine the heat transfer. They're both square roots, width and wind. Because it's proportional to width, now we look at shapes of leaves. And the textbook has some examples of shapes of leaves, but imagine, I'm going to put this up here, some giant banana leaf which would have poor heat transfer characteristics versus some leaf that might look like that. This has much better heat transfer characteristics. And in fact, how about a grass leaf? I guess grass would do grasses vertically. Grasses are thin, and thin grass leaves have better heat transfer characteristics than wide dicot leaves. And grasses grow more commonly in arid places. You don't see big tropical leaves like this in deserts. You see very thin leaves because they're out of water and they don't want to heat up. They want to be able to blow the heat away. So this becomes really fascinating to think about the shapes of leaves and how well they avoid getting hot. And if they can avoid getting hot, they can avoid using water too, if they can blow heat away. So we have width and wind in this. The rest of this is coefficients to put units on these. After we get the concepts, then you look up these coefficients in a book. But to do this to be equal, now we have a coefficient right here. Make sure that I'm following my notes. I am. 0.04 times, and because of the rules of algebra, we can do width and wind right here. So there's boundary layer thickness. And this, in these units, this is boundary layers thickness in meters. So it's going to be a small number, a real fraction of a meter. Width has to have units of meters, and wind is meters per second, which are the standard units you put those in. And this has units to make this all cancel to get to meters here. So what's this number right here? Why is that 0.004? This is a coefficient that, a variable coefficient depending on surface roughness of the object. If it's some polished metal, it's a different coefficient. This can vary from over a factor of 2, 0.002 to 0.008 even, depending on how rough the surface is. You can imagine if a leaf is hairy, we call that pubescent, and some leaves are really pubescent. They look like they have fur on them. In those leaves, this might be 0.008 because of trapping air. Some furry animal, this might be 0.00, I don't know how high a furry animal can get, but danged high, I'm sure, versus a real smooth surface where it might be lower. So the textbook uses this number, and it's a general number for typical leaves. It's higher in hairy leaves, and it's a little lower in real smooth, glossy leaves. But for these purposes, we use 0.004. Now we get a thickness of the leaf in meters. Let me keep going, and I'll come back to some filled-in examples of this. But we still haven't solved this whole thing, because what we want to know up here, I'm going to erase, now let's leave latent and sensible. What we want to get to up here is watts per meter squared. And so far all we know is a thickness of the boundary layer. So to put this whole thing in perspective, I'm going to erase these leaves. We get c squared, could write this anywhere, delta t over boundary layer thickness in meters, delta t in degrees Kelvin or degrees C, it doesn't matter, it's the same number. Now we have 0.026 in here. This is the thermal conductivity of air. What's the resistance to heat flow for air? So, and this has units to make all the rest of this cancel, and I'll give you a handout with worked out units. But if the air density was really low, almost a vacuum, this number would get bigger, and if it was more dense, it would get higher. This number varies slightly with humidity of the air and temperature, but not very much. It's close to this number. So now we can put numbers and solve this, but there's one final coefficient. Remember, for net radiation, we had two sides of the leaf. That long wave can go up and it go down, and that's a good thing because it helps leaves cool off. If we ran these numbers for the parking lot outside, now we don't get to have two sides of a leaf because the parking lot can only go up. Parking lot would have a big storage component below, but in the case of a leaf, there's two sides. Guess what? For conduction and convection, two sides of the leaf. So right here, I'm running out of room. 2 times thermal conductivity of air times the delta T times the boundary layer, and now we get watts per meter squared of heat transfer from that leaf. And the beauty of this is now we have everything in watts per meter squared. Watts per meter squared, watts per meter squared, watts per meter squared. And now we can look at balancing the energy, what the leaf is doing. So I have a handout of this. It's adapted from the book. And oh wow, we got this is up here. We're all set. This is the same thing I wrote on the board. So my goal is to show it and then follow up with the written difference for this. So this is the equation, and on the bottom of this, actually not the bottom, it's at page 2, this is a few examples I've written on here. Just a worked out table. Leaf width or length. Now what this really is the shortest dimension. People talk about length, but a grass leaf, it's the shortest dimension because it's generally blown sideways. So here's a banana leaf, 0.5 meters, right? So that's a big leaf. The boundary, this table is boundary layer thickness in millimeters. A banana leaf with really low wind, wow, almost a centimeter. Being a banana leaf this is almost like having a thermal pane window around the banana leaf. A centimeter of 8.9 millimeters is pretty thick. So that would not stay in equilibrium with the air very well at all. It would heat up, and it would have to evaporate water to balance the energy because it's so well insulated. Now we go up this way, and a real thin leaf, 0.002, this is meters, so now this is like a pine needle up here. And now that boundary layer is real tiny. And we go this way, and these are very still air. This is meters per second. 1 meter per second is, down in here, smoke would rise vertically. And 1 meter per second is, well, cup anemometers. As you all know, it takes somewhere around 0.4 meters per second to start turning the cups on a cup anemometer. Depends on the instrument, but so this is very still air. Now we get up to 10 and it's really breezy, and all these numbers are small, so leaves are going to always be very close to the air temperature when the wind is blowing because of this gets tiny. So now let's look at this example. It's just one where I've put in the numbers and worked this out. I assumed a delta T of 2, that's pretty typical in the middle of the day, a 5 centimeter width, so how long is that? 3 fingers? It's just some average dicot leaf. Somewhat still air. The wind is blowing, but not very fast, so now we plug in the numbers, and there's the boundary layer thickness. And here's the rest of it. We get 116 watts per meter squared transferred by conduction and convection in this example. So just to put this in perspective now, we got this. I'm going to erase this. I'm going to erase this. This. Let's try red. Remember from a few lectures ago, we put some typical numbers in here. And this was from the handout. This is 375 watts per meter squared. We don't know this. We're trying to solve for this. 116. So it's pretty easy arithmetic now. 275, 265, what would this be, 259? I think that balances the equation. So this would have to open its stomates and evaporate 259 watts per meter squared to balance this, assuming there's not storage and all the other stuff. So example of balancing this after we've put the numbers in for conduction and convection. Now, I want to show.
The 259 is what you would do pass backwards to get the stomatal resistance.
And yes, now that we've solved this and we know this has to be this, so let me repeat the question. Could you then use this to calculate stomatal resistance or stomatal conductance? And the answer is absolutely, and that's how we do it. Because we get the driving gradient for this, and the only variable left in this whole thing is stomates. And then the stomates had to be this open to be able to balance the energy. And then once we do that, of course, then we make models and say, in this condition, the stomates were like this, and then we try to take our models and put them in and see if the whole thing balances. But that's the beauty of energy balance, is we calculate these three numbers and balance the energy. I have another handout. This is a two-sided handout. This is entitled A Six-Step Procedure to Determine Energy Balance Components in a Leaf. So it's all in one page. Just do this, condensed. Incident is dependent on short wave. By the way, we often use the Greek letter phi to mean radiation. I always use a capital R, but it's the same thing. Phi is radiation. That's short wave in, plus short wave reflected, plus long wave from the sky, plus long wave ground. Those are the four components. And the sky component we measure directly. The reflected we calculate times this is 1 minus the albedo of the ground. The sky, see how I've crossed this out? Well, we used to calculate the sky, but now it's becoming way more common to use an instrument and just measure it directly, because we don't have to try and model the sky. And here is an example of a new model instrument to do this. There's several companies that build these. This is one more compact one. So you can see this has 4 sensors, 2 on the top, 2 on the bottom. This does all of these components of net radiation. This sensor outputs this number. So all in one, you get this number from a single sensor. Short wave in, short wave out, long wave in, long wave out. This one's called a 4-way radiometer. So if these instruments are accurate, wow, we've skipped a lot of modeling to do this. See, even here, I have calculate the ground based on ground temperature. Well, now we could cross that out and we could measure. So if you have an instrument to measure it, great. If you don't, you have to calculate it. So we keep going down on this. Step 2, now we do absorbed radiation. And then we do emitted long wave, again following the same. Boom, step 4, determine net radiation. So on the first page we got to 375. And this doesn't have an example numbers, it's just a summary. Now flip it over. Step 5 is what we did previous lecture. Energy transfer from transpiration. Here's the equation. It's either divided by resistance or times conductance. Now I did an example here. No, I didn't do an example. I just put the equation. This, I had to cross these out because this is the latent heat of evaporation right at air temperature. This is not incorrect. It's just a more detailed equation. And let me see if I've got my example of that. I'm not sure I can find that quickly. It's just a chart. Let me show you what this chart looks like. It's the latent heat of evaporation. So this is 2, I'm running out of room, 2.45 megajoules per liter, latent heat of evaporation. What does this line look like as water heats up between 0 and 100 degrees C? At 0, this is 2.25 degrees, all the way from freezing, and at 100 degrees C, oops, sorry, it goes the other way, 2.25 at 100 degrees C, and at 0 degrees C, it's, I don't have the exact number on here, but it's about 2.5, something like 2.55 maybe. The point is, latent heat of evaporation varies very little with the initial temperature of the water. It varies a lot with the change of state of water. So if we connected our dots, this would be our graph of the effect of water temperature, temp, on this coefficient, latent heat. And because our measurements are all right in here somewhere, for sure they're all 2.4 something, 2.46, 2.43. So I simplified this to 2.45. I'm going to come back to this now in just a minute with application at night. Now we do conduction and convection, and here's the rest of it's just a one-page summary of this whole thing with delta T. Let's take these principles now, and now I'm going to show a couple more things on this before I do this. These are just examples out of the textbook that are useful examples. Here is the length or diameter of an object and boundary layer thickness. And in millimeters, you know, I always think I'm a ruler and looking at the ticks on a ruler. I can conceptualize a millimeter. Don't ask me to conceptualize a micrometer. Those are too small to see. But 1 to 3 millimeters. Now look at how this curve changes with shape. A flat leaf is different than a sphere, and that's different than a cylinder. So we can use the same equations to model all kinds of things. Cylinders and different shapes, different roughnesses. But this is how those shapes affect it. And then here's just wind speed examples for tables of examples of that. Here's a good example of why width matters. Here's the wind. We have laminar flow in the beginning. It goes turbulent at the end. And the heat transfer is better in this first section than it is down here at the end. That's just an illustration of that. And I'm sure in a class, in a heat transfer class, you go over all this stuff in great detail. And all this stuff is done in wind tunnels to calculate the heat transfer characteristics of things. So we put leaves in wind tunnels to do that. Now I want to go to this little diagram here. I'm going to blow this up big. It's a simple diagram. I'm going to have white underneath it. Make it big. I'm pretty convinced that if you make everything big, it gets easier to understand. And I think that's why that guy, Macaulay, he writes those books and he takes, how does this work? And he makes it big, and then you can understand it. And I'm pretty sure if you just can make the diagram big enough, it's like a kid's book, and you can understand complex things just by making them bigger. So here's big. Here's an example out of the book, daytime. Net radiation, and here's the conditions here that we've measured with our instruments. 370 N, well, coincidentally, we got 375, but they're similar numbers in the day. By the way, this number in the day probably goes from 300 to 500. It depends on the conditions, but it's in that general ballpark. Obviously, if it's cloudy, it's a lot lower. And it depends on the surface it's over. But it's in the neighborhood of 300. Okay, that has to balance. So in this example, the leaf here is 5 degrees above the air. So this is 180. And we did 116 because the wind wasn't blowing very much. So 190 for transpiration for the leaf. We can put in water flux density 4 millimoles. And I don't know if I want to take the time to work that out, but 4 millimoles of water. This is a transpiration rate measured of the leaf. Now that would have to be measured to get this. Times 18, water is 18 grams per mole. 18 grams, so 64 milligrams of water, 40, it's more than that, 72? 40 plus 32, 72 milligrams per meter, everything's per meter squared per second of water. Now, times 2.45, and this is a milligram, we're going to have to scale this way down, is a, let's see, a milliliter, liter, thousands. It's not a milliliter, it's a microliter of water. So now we have 2.45, and I'm going to do kilojoules per milliliter. Or to get the microliters, let's get rid of the kilo, and this is going to become microliters. So the latent heat of evaporation, conversion of units, 2.45 joules per microliter of water. This is the measured transpiration rate. Now what do we get here for joules? 140. Anybody want to do the math? It's going to be about 190 joules per meter squared per second. Probably maybe exactly 190. So we just did an example of taking a transpiration rate in moles of water, converting it to weight of water, multiplying by latent heat of evaporation to get this number. It's a good thing that worked out. I just thought of doing that right now. Okay, this is typical. If the plant is well watered, this can get to 370 and this one can go to 0. And when that happens, the leaf is at the exact same temperature as the air. As the plant runs out of water, this has to get bigger until, if the transpiration went to 0, this would have to roughly double, and the leaf temperature might be 10 degrees C, the leaf to air delta T, to make the energy balance. A little bit more radiation is lost if the leaf gets hot, but not much. So you can see how these numbers go back and forth constantly, depending on how well watered the plant is. And this is why, if we put infrared sensors on this to get leaf temperature, we can tell the water status of the plant. We can tell how out of water the plant is. Now, here's the next big thing. Radiation frost, taking these things at night. Here's the moon. He didn't get that sun anatomically correct, but we could fix that right here. I don't really want to draw on the board, but there. Now, you've got to be happy when the sun's out. So here's the moon at night. Well, guess what? This net radiation goes to 0, and the sky is cold. So on a clear night, net radiation is always a negative number. Assuming the ground is colder than the very cold sky, it's always a negative number. Energy still has to balance. So now, these numbers that were going out of the leaf in the day are coming in to make the energy balance. This one's easy. It cools off below air temperature, so it's gaining some heat. Everything reverses itself at night. What's going on here? A negative number. In this case, C is transpiration. I'm not sure why I use the symbol C, but this is transpiration. It's a negative number.
L is transpiration.
Oh, thank you. Thank you, Mark.
C is conduction.
Yep. So L is latent heat, and C is conduction and convection. So here's a negative number. What's going on here? It's evaporating water. It's cooling. It can go to 0 if the stomates are shut. How'd this go negative? Condensation. Frost. This is a cold night. The air temperature was +1. The leaf cooled to -1. And water condensed on it, and it was below 0, so it became frost. And this is exactly what makes frost form. So what happens here is the leaf gains heat by change of state in water. And I have a handout right here. This is a whole page handout. But again, to make it big, or to make it easy, it's big. So here we go. Change of state of water. Once you get this, you have it forever, but it's counterintuitive to people when you first think about it. Heating up water really doesn't take all that much energy. The energy is in change of state of the water. So the energy required, megajoules per kilogram, to heat water from 0 to 100 is 0.42. No change of state, or there's a big change of temperature, but no change of state. To evaporate, here, let's do the liquid to gas. To evaporate it here, after it's at 100 degrees, 2.25 megajoules per kilogram to evaporate it. So it takes more energy to evaporate the water than it did to heat it from 0 to 100. A lot more. What's that, 5 times as much to evaporate the water? So the big cooling is when the water evaporates. Here, now I can fix my graph. At 0, no, this is 100. Nope, I got it right. At 100 degrees, it's 2.25 to evaporate the water. So now we go the other way. Same thing happens with ice. Now it's going, change of state from a solid to a liquid back and forth. Ice, it also takes more energy to freeze the water than it, almost as much, to freeze it as it did to cool it from 100 to 0. So every time when I saw this many years ago, and I'm thinking about it, and I think about every time, now I have a fridge automatically makes ice, but you put ice in your ice cubes and you put them in the fridge and you're waiting and waiting and they're cold but they're not freezing and then you wait and bam, they all freeze at once. And that's because this went fast and that final thing took forever to change the state of the ice cubes. In fact, speaking of that, there's a famous question. I've never actually done this experiment. And you make ice cubes out of hot water and cold water and put them in your fridge. Which one freezes first? That's what you would expect.
I've done this test myself.
And which one freezes first? Cold?
There's a content of energy you still got to pull off.
That's right. Intuitively, the cold water is a lot closer to starting. But what can happen? This is the little trick in this question. You put that hot water in there, and it can evaporate like crazy. You put an inch or a couple centimeters thick ice cube in the hot water in the process of cooling, loses energy like crazy. So now your ice cube is only 1/4 of an inch thick, and you only have to freeze 1/4 of an inch. So supposedly you can make ice with hot water and it'll freeze faster, but you won't get much of an ice cube because all the water evaporated. It was all the energy is going here. But the goal is to have big ice cubes, so you always start with cold water. But there's the principles back and forth, and the bottom of this has this, by the way, this, when it goes this way, this is called the latent heat of condensation, and this is latent heat of evaporation. So we get dew on leaves, it heats them up, that goes back and forth. Now we can go from this to one table in the book that I'll go over just a bit quickly here, but this is the same diagram that I just showed you big. This is page 332, figure 710. Nobel works out 4 examples with inputs and outputs from leaves. Here's his assumptions down here. It says first one, sea level, cloudless day, 840 coming in. So this isn't quite 1,000. It's not quite full sunlight. But he ends up with net radiation of 370, which he uses up here. And he's got the components of all the things in and out on here. Then he goes to 2,000 meters. So now the incoming radiation is a bit more. The sky is slightly colder. The end up net radiation's the same. Here's the key, leaf temperature. This is +5. But at 2,000 meters, the leaf temperature is a little bit colder. The sky is a little bit colder and the leaf is a little bit colder. Then he does, and these lead to thousands of interesting test questions. Then he does a silvery leaf where the emissivity and emissivity changes and the albedo changes because of a silvery leaf. And all of a sudden, this is on a 2,000 meters, 10 degrees, and the leaf still heats up 3 above the air temperature, but the heating is less because the leaf is a different color, more silvery. And then the last 2 are really interesting. Sea level, Cloudy night. So now it's all zeros here because it's night. Temperature here is 1. This is example you worked out up here. When there is wind, the leaf still froze. A light wind, the leaf still froze, -1. But then he works out an example right under it with no wind or minimal wind, and the leaf went to -9 below the air temperature. And that is the definition of a radiation frost, which I put right here. When a surface goes below the air temperature and below freezing, frost forms on it. And it happens all the time on clear nights because they get below the air temperature, there's condensation, and the condensation freezes, and that's what frost is. And if it happens all night long, the frost can get enormously long. But it's all because of this radiant cooling at night. This is so profound that this is, I'm going to pick this up in the second half of this, but I'm going to introduce it here. This is so profound that fruit growers in the spring have to be continuously worried about radiation frost. In the past, they've just looked at air temperature, and in one night, they can lose $1 million worth of fruit because their young flowers get cold and they freeze, and they're done. Their yield is done for the year. They cannot afford to just do frost protection based on air temperature. They have to do it based on surface temperature of the, and particularly in their case, of the flower buds. So you can buy an instrument that's a black flat plate that simulates a leaf at night and put it out, and that flat plate gets colder than the air, and attach a sensor to it, and then also a single black sensor that in a sensor give a grower a sense of the radiation frost from a direct measurement, as opposed to calculating it with all the other parameters of a weather station. Fruit crops in Utah are a much bigger agricultural sector than most people realize. Michigan and Utah are the two top producers in the nation for tart cherries. It's a multi-million-dollar industry, and it's all concentrated here in the northern part of Utah. So in recent years, we've done a lot to help fruit growers tell when to protect against radiation frost. So I'm going to stop here with this section, especially since I made it to my end of my list. And after break, we'll pick this up and talk about the applications of radiation frost and summarize all of the lectures with examples of this. So, and I think we have some sandwiches.